Hello, my name is Joe Chacon. I'm an electrical engineer with Padge LLC. This is the fourth of several videos about harmonics. Today, I want to talk about the effect of high harmonics on transformers and give an example. I must clarify that I'm not a magnetic design specialist. I do all right with applications of magnetic devices, but not with the design itself. Please look back at the first video of this series to understand what harmonics are. We will use the example we started in the first video to carry over into this video. Let's start at the highest level and talk about how harmonics can be damaging to transformers. The first issue they create is higher heat loading. We will dive into that in significant detail. The second issue is they produce higher voltages that can compromise the dielectric integrity of the transformer. Remember, the voltage example from video one that had the waveform of 480 volts AC with 3% on the fifth harmonic, 2% on the seventh harmonic, and 1% on the 11th harmonic. Recall that the fundamental created a peak voltage of 678.8 volts, and the small harmonics made that peak voltage 680 volts. If we made the fifth to have 30% of the fundamental, the seventh to have 20%, and the 11th to have 10%, then that peak voltage would be 809 volts. That is a substantial voltage increase of 19.2%. The plot will look like this. Looks quite wicked, doesn't it? So we've seen how harmonics can cause higher voltages. That can cause dielectric breakdown on transformers. Let's look at how they create excessive heat. Consider this transformer equivalent circuit for a transformer. The transformer is a three-phase transformer rated for 225 kVA. Secondary voltage is 480 volts AC Y. Primary voltage is 34.5 kV delta. The secondary current is 60 hertz. Is easy to calculate. It is the line to neutral voltage divided by load resistance. 277 volts divided by 1.07 ohms is 258.88 amps. The copper losses are also easy to calculate. It is the current squared multiplied by the Req prime resistance. This value is 686.3 watts. It is three-phase, so we multiply by 3 to get 2058.9 watts. The core losses are also easy to calculate. It's the line to neutral voltage squared divided by the R0 prime resistance. This value is 375 watts. It is three-phase, so we multiply again by 3 to get 1,125 watts. The total wattage loss to the copper and core is 2,058.9 watts plus 1,125 watts, which is 3,183.9 watts. We call that Q. We're going to stay with the example we've been using for several videos now. The fifth harmonic's 3%, the seventh harmonic's 2%, and the 11th harmonic is 1%. This chart shows the respective copper losses, core losses, and then total losses. The total loss is shown as three-phase, whereas the copper and core losses are shown as single-phase. Okay, let's assume the transformer has a surface area of 7 meters squared. We'll call A. It has a heat transfer coefficient of 7 watts per meter squared Kelvin. We'll call H. These are reasonable assumptions for a transformer this size that is cooled natural air convection. Delta T is governed by this equation. Delta T is equal to Q over H times A. Delta T for the fundamental is 65 degrees Celsius. Delta T with harmonics considered is 66.3 degrees Celsius. This is pretty benign as we'd expect because we know we're IEEE 519 compliant. So suppose our fifth is now 30%, our seventh is 20%, and our 11th is 10%. Our Q goes to 9,569.7 watts, and our delta T goes to 195.3 degrees C. Wow, that's going to hurt our transformer. There are a couple of other things going on with harmonics and transformers that I didn't even touch on. I didn't talk about eddy current losses nor hysteresis losses. These both compound the heating effect. I'm sure there are even other things going on that cannot be good for the transformer, but I've mentioned the ones that I'm most familiar with. So, what can we do with our transformers when we know harmonics are present? I plan to address this in future videos, but one thing I will mention here is a higher K factor. A K factor is a rating of a transformer. That means the transformer designer has made the transformer specifically to handle that heat or dielectric stress. A K factor of 1 means the transformer is only rated to see non-harmonic loading, also called nonlinear loading. Let's consider the same example we've been working on, but let's keep that fifth harmonic at 30%, the seventh at 20%, and the 10th at 10%. The K factor for this type of nonlinear harmonic loading would be 6.42. If I were specifying the transformer, then I would specify one at K factor 13 because that is the next size up. Note, if we went back to the example where the fifth was 3%, the seventh was 2%, and the 11th was 1%, then our K factor would only be 1.054, making the K factor 1 sufficient. I hope it is a bit clearer as to how harmonics can adversely affect transformers through heat and dielectric stress from higher voltages. I hope this knowledge can help you become the harmonics guru in your company. Please look us up at padge.org. That's padge.org if you need anything on this topic or others.